Maybe you've already tried the Practice FRQ, and if you have, I'd like to just kind of go through it quickly and see if there's anything I can help understand. First thing about this is that there's a problem where we have the percent composition given. We're going to turn that into an empirical formula. That's one type of problem. Then we're going to take a hydrate and use the dehydration data in order to calculate the formula of the hydrate. And the last thing is, since you are using a burner in this lab, then we thought we should talk about Bunsen burners anyway, at least where the hot part of the flame is. The overview of the problem here, so it says a hydrate has all the water driven off, and the anhydrous compound is found to contain a certain percentage of magnesium, sulfur, and oxygen by mass. We're going to turn those into grams and turn them into moles. Then you will use that to get the empirical formula. Then the second part is we have the mass of the hydrate that's heated to begin with. Afterwards, we get a certain amount of the anhydrous compound. We can subtract to find the grams of water, and then we're going to get moles of water, and then we can use that to get the formula of the hydrate. And the last part is about the Bunsen burner. So if we start and say, well, here are these percentages, if we assume that we have 100 grams of substance, then these percentages turned into masses. So we have 20.2 grams of magnesium, 26.6 grams of sulfur, and 53.2 grams of oxygen. Now we're going to change each of these into moles. We're just going to use the atomic mass. So we'll look on the periodic table and see that that's 24.31 grams for 1 mole. And for this next one, for sulfur, we will use the number 32.07 grams for 1 mole. These are the atomic masses of magnesium and sulfur. And we have oxygen. We use 16.00 grams for 1 mole of oxygen. Now make a little point here about the oxygen. Most of the times, if we see oxygen in a compound, in a problem, we're talking about diatomic oxygen. And in that case, we wouldn't use 16, we'd use 32 grams per mole. But for this kind of a problem where we really want to get a formula, and if we want a formula, we're going to have moles of atoms, atoms, atoms. So in this case, we're going to have to do not the molecular weight, but the atomic mass of this. This is the one time where we do that. So we work out answers, and we find out that we get 0.830 moles of magnesium. We get 0.829 moles of sulfur, and we get 3.325 moles. Okay, I'm going to fix that up. Okay, 3.325 moles of oxygen. So our compound has magnesium, sulfur, oxygen, and it's in these ratios. So we're going to take all three of these numbers and divide them by the smallest number, which is the 0.829. So we can see that this will turn into 1, this one will turn into 1, and I didn't leave myself enough room, but if I say 3.325 divided by 0.829, that comes out to be really close to 4. So my formula then is MgSO4. And that's the first part of the problem. Determine the empirical formula of the compound. Second part now, if we were to heat this hydrate, then in the little crucible, we're going to put in the compound, which is magnesium sulfate with water. And that's the number here, 12.970. And then we're going to heat it. And as we heat it, the water is driven off. And then what we're left with in the bottom is 6.335 grams of the anhydrous compound, in that case magnesium sulfate. Now notice that if we were looking at data, the way this is stated here, it says the final consistent mass. So if we were to weigh it, then weigh it again, weigh it again, weigh it again, we'd expect it to get smaller and smaller, and we would keep going until the last 2 or 3 values come out the same. That way we know that we have driven off all of the water. So calculate the number of moles. Well, first we have a subtraction problem to do, and that is we have 12.970 grams of the hydrate, and that represents the compound, the magnesium sulfate and the water, and we're going to subtract the 0.6335 grams, which was the magnesium sulfate anhydrous. So what we get left over, which is 6.635 grams, must be the water. Now, just like we've been doing here, we're going to say 6.335 grams of magnesium sulfate. We got to add it together a magnesium, a sulfur, and 4 oxygens, and when we do that we get 120.38 grams for 1 mole of magnesium sulfate. When we do this problem, that comes out to be 0.0526 moles of magnesium sulfate. Now, if we do the same thing for water, we'll divide by the mass of a mole of water, which is 16 plus 1.01 and 1.01. We get 18.02 for 1 mole of water. And when we do that calculation, we get a number 0.368 moles of water. Now, for part 1, or part I of this problem, that is what we're looking for, so that's our first answer. And we want to continue and get the formula of this hydrate. So the formula of the hydrate is going to be the ratio of the moles of water and the moles of magnesium sulfate. So we divide them both by the smaller number. Obviously the magnesium sulfate will come out to be 1. And if we divide this number by 0.0526, we get a number that's very, very close to 7, 6.99 something. So that means our compound then is magnesium sulfate dot 7H2O. We would call that the heptahydrate, magnesium sulfate heptahydrate. The last little piece of this is talking about a Bunsen burner flame. And a Bunsen burner flame, it has the big outside cone, and then inside there's a smaller cone. Right at the very tip of that cone is the hottest part of that flame. So I finish off my Bunsen burner. So you can see that here in our picture, that if you were to move this little piece of metal up and down in the flame, it gets the red hottest right at the very tip of that inner cone. That's it.